Hello, welcome back. This is try number 2 on this lecture. The first one that most people were a part of didn't record correctly, so I am recording this. We have a few people joining us. And I will be going back through Unit 1, Part 2, which mainly focuses on electrostatic forces, the difference between the types of forces we're interacting with as far as when we have protons and electrons within an atom. How do we use the concepts of those forces, how they interact, how we use them to justify atomic size, how do we use it to talk about ionization energy, electron affinity, what do these do for us? So the main one we're going to focus on today is size, because the size of an atom or its atomic radius, which is essentially the same thing, the atomic size is very important in justifying other properties such as ionization energy, electronegativity, bonding preferences, things like that. So we'll get right into it. A couple things to define early on is electrostatic forces. Electrostatic is essentially the same thing as Coulombic forces, and electrostatic forces in general, the attractive or repulsive force between charged particles. And then Coulomb's law is more towards calculating the actual force of attraction or repulsion between particles. But we use the word Coulombic forces or electrostatic forces. They essentially mean the same thing. So let's throw a color here you guys can see. So if I say Coulombic forces or electrostatic forces, they're representing the same thing. So in general, when we have oppositely charged particles, there's a force of attraction between them. And then when you have like charged particles, like two positives or two negatives, then there's repulsive forces. And that's just a general concept that you've heard before. The large thing that affects the strength of these forces is distance. So if the two particles are really close together, they're going to feel that attractive force or that repulsive force well. As they get further and further away from each other, the attractive force, I'm specifically talking about protons and electrons here. Let's assume we're talking about protons and electrons. As these protons and electrons, the distance between them increases, then the attractive force between those two particles significantly decreases. And this plays a large part into why atoms get larger as you have more and more energy levels. This is the attractive forces are changing with the distance. I've attached a little video here that you can pick up when you look at the PowerPoint. This is a demonstration of Coulomb's law and charged particles attracting and repelling each other, so you can watch that on your own. And again, Coulombic forces and electrostatic forces are interchangeable for our purposes. The same way that atomic size and atomic radius are interchangeable. They represent the same concept. So one of the big ones that we're going to get into early on that helps us define size is electron shielding. The idea is when you have an atom, here's our nucleus, the first energy level is a 1s orbital, and it can only hold 2 electrons. Once a shell is full, it actually causes a shielding effect, which kind of cancels out some of the positive charge in the nucleus. So any additional electrons feel the pull from the nucleus less. So once we get to that 2s and 2p electrons in the second energy level, they feel the pull from the nucleus less than the 1s electrons because of this shielding effect. The 1s electrons are shielding the outer energy level from the nuclear pole. So let's say we have 4 protons. We can call this a +4 nucleus. The 2 electrons from the 1s orbitals will shield off essentially 2 of those protons, because electrons and protons cancel each other out. And so the 2 extra electrons, say this is beryllium, the 2 valence electrons for beryllium feel less of the nuclear pole than the 1s electrons for beryllium. And this ultimately allows the electron to the electrons to exist further from the nucleus. This is why atoms get larger with more energy levels. As you go down the periodic table, the atoms get larger because they have more energy levels, and those outermost energy levels have a greater shielding effect from the inner full shells. And just to show relative sizes, we have 1s, then 2s, 3s, and so on and so forth, the increasing size based on the number of energy levels. And this is looking at group 1 with the hydrogen, then the rest of the alkali metals going down. Another thing to mention is, actually that's pretty much it. This diagram, this is another diagram just to show the electron cloud, where it's not exactly these orbits, there's not these rings around the nucleus, it's more of an electron density where the electrons are most likely to be. So this second diagram kind of shows the electron cloud a little bit better. And we're largely using this trend, electron shielding, to describe why atoms get larger just going down the periodic table within the same column. As we're going left to right, we have a different trend that we'll use. I'm a little bit more on electron-proton interaction. This just shows some of the attraction and repulsive forces going on within the atom. The repulsive forces between electrons we're really not going to be considering right now, mainly because those help direct the atom or the bonding angles between atoms. So when we have something like water, why is it at a particular angle, where the bonding angle's like a little less than 109? That's because of the electron repulsion. But right now, in terms of just electrostatic forces, we're not really going to be worried about the electron repulsions between other electrons. We're mainly going to be focusing on how far the nucleus is from valence electrons as that electrostatic attractive force. Okay, so the other pattern that we're going to be using to talk about differences in sizes is effective nuclear charge. So there's essentially two things that we can pull from. We've got the electron shielding as you go down. Let's draw a little periodic table. As you go down, the atoms get larger due to an increase in shielding. So the atoms get larger as you go down a periodic table because there's more shielding. And then as we go left to right, we're going to be talking about effective nuclear charge. So these are going to be elements in the same period. There's a cool analogy for this one that I found online, so you can pull up the PowerPoint and look at this video as well. But in interest of time, I'll just go ahead. So there's this little bit about effective nuclear charge as far as calculating an exact number. I didn't do that a whole lot in the class because you can effectively get the same result by just looking at the total number of protons instead of subtracting off inner core electrons, which is mentioned right here. So take this with a little bit of salt because it's useful, but I think you can still get the same result by just looking at total number of electrons or total number of protons instead of subtracting off the inner core electrons. So I'm not going to talk too much about what's written here. You'll get it in textbooks and online if you look up effective nuclear charge. But essentially what we're going to be doing is taking relative nuclear strengths of two or more atoms and saying, we have these two atoms, different elements, which one has the stronger nucleus? And that is going to affect the size of the atom based on how attractive the electrons are to the nucleus. So effective nuclear charge. For the example we're going to see today, we're going to compare carbon to oxygen. And we're going to be able to say that oxygen is smaller than carbon, even though we can see on the periodic table that oxygen is further to the right than carbon, meaning oxygen has two more protons, two more electrons in the neutral state. Oxygen is still a smaller atom in terms of where the electrons are able to exist. So what we can do is talk about, okay, we can say carbon, we have oxygen, we can list out the properties that matter. Carbon has 6 protons and 6 electrons in the neutral state, and oxygen has 8 and 8 respectively. So Why is oxygen smaller if it has less stuff? Well, it has a greater effective nuclear charge. It has a stronger nucleus. These 6 electrons and these 8 electrons are very close in electron configuration. So they're both on period 2, so they both have 2 energy levels. Carbon has 4 valence electrons, 2 being inner core electrons, so the 4 are outer valence electrons. And oxygen is going to be a little bit smaller, so I'm going to draw it somewhat respective in size. And so oxygen has 6 valence electrons. Because oxygen has a stronger nucleus, more protons, and because they have the same energy levels, even though oxygen does have a few more electrons, they're still on the 2nd energy level, which we labeled as n equals 2, that outer energy level. The stronger nucleus is actually going to pull these electrons in more on the oxygen. These electrons feel a stronger nucleus, and so they're pulled closer to the nucleus. That's why oxygen gets a little bit smaller. The nuclear charge of oxygen is greater than carbon. Carbon's 4 valence electrons can exist further from the nucleus because it has a weaker nucleus. So this pattern is mainly used to justify why oxygen is smaller than carbon. These 2 elements are on the same period. So we're only using really relative nuclear charges if they're on the same period. You're not going to see too many examples where you're doing diagonal comparisons where we're saying, okay, we have boron, which on the periodic table marking, we have boron versus like selenium. They're diagonal to each other. Which one's larger, which one's smaller? There's not a whole lot of diagonal comparisons. It's either vertical or horizontal comparisons. In general, let's say you have something like oxygen and chlorine, they're pretty close to each other. In general, 3 energy levels is going to be larger than 2, as opposed to the left to right rule. So the top to bottom rule is more important than the left to right rule in terms of the number of energy levels. Okay, so we went over atomic size by using shielding and using effective nuclear charge. Once we're able to comfortably predict the size of atoms, the relative size of atoms, that helps us make predictions with ionization energy and electron affinity. The size is a very important factor, where those electrons are positioned. So, ionization energy is defined as the energy required for an electron to be completely removed from an atom, which is often referred to as binding energy. So binding energy and ionization energy essentially refer to the same energy value. The energy of the electron, and we can measure that electron's energy by getting it to be completely removed from the atom. And what you could expect is, let's say we have an atom with 3 energy levels, let's say sodium, whereas 1 valence electron, and then has 2 full inner orbitals. We have n equals 1, we have 2, and we have 3 as far as the number of energy levels. The distance from the nucleus directly affects the binding energy. So the electrons closest to the nucleus should have the highest binding energy or cost the most energy to be removed. So that's why we don't really see a whole lot of first energy level electrons being removed, because if given a choice, there is a lower energy electron on the outermost energy level. So that 3s electron here is going to have a lower ionization energy than a 1s electron, mainly due to where it's located. 1s electrons are really close to the nucleus, costs a ton of energy to be removed. 3s electrons are going to be the furthest from the nucleus, lowest binding energy, lowest ionization energy. Just comparing electrons within the same atom. So we see the outermost electron being the first to be removed. And we call this the first ionization energy when we're removing 1 electron, the first one. Now sodium, when an electron is removed, we say it's ionized. And then in this case, because it only has 1 valence electron, this entire 3rd energy level essentially disappears, and then you're left with 2 full energy levels, and then we say it has a charge. These are some pretty early on basic concepts that we went over, but it's helpful to review. Pulling a table from the internet, which can come out of a textbook. Here's a table of ionization energy values. So you can see when this might be a table that's given on a test that you have to read, or these are values that might be given. This first column is just the first ionization energy. So these are the first electrons to be removed. And these are all elements in period 3. These are all period 3 elements. So sodium has 1 valence electron. And we have magnesium with 2, which is why we see 2 values before this blue section. Aluminum has 3 valence electrons, which is why we see 3 values before we get to that blue section. So another pattern we can notice here is, let's focus on aluminum. Aluminum has 3 valence electrons. So we have first shell, second shell, and third shell. The 3 valence electrons are going to be drawn on the outside, and we're going to kind of ignore the ones on the inside, even though they're full shells. The first electron to leave is going to cost the least amount of energy, 578. Once that electron leaves and it's gone, the nucleus, even though it has 13 protons, that number of protons doesn't change. The number of electrons reduced. So each of those remaining electrons feels a stronger pull from the nucleus than before. If you think about 13 protons, 13 electrons in the neutral state, each proton matches up 1-to-1 with each electron. But when we take an electron away, now we're down to 12, the plus 13 charge of the nucleus is now spread out between fewer electrons. Each of those electrons feels a greater pull. So every time an ionization happens where we remove an electron, all the remaining electrons on every energy level gets closer to the nucleus. Another pattern you can see here is the difference between, looking at aluminum again, the third ionization energy and the fourth ionization energy. Once aluminum loses all 3 valence electrons, the next fourth ionization would come from a complete inner shell. And that costs an enormous amount of energy compared to the previous ionizations. So we really only see aluminum going to a +3 charge because it's really only going to lose 3 electrons under normal conditions, where that fourth electron isn't necessarily going to be removed. If you throw enough energy at it, you can get it to ionize to a +4, but we don't see that happening under normal conditions. So what we can do is express each of these ionizations as a chemical equation. And I took the numbers off of the chart to represent as enthalpy values. And these are all going to be positive. The atom is going to absorb energy, specifically the electron is going to absorb energy, and if that energy is sufficient enough, then the electron can leave. This energy can join the atom from a variety of sources: heat energy from a chemical reaction, photons of light coming in, and the electron being absorbs that energy, converts those light energy into potential energy used to get the electron to leave. A variety of sources, but we have measured values, increasing values, as we can see, on the subsequent ionizations. And we really are ionizing one at a time. First electron leaves, atom gets a little smaller. The next ionization costs more energy. Then atom gets smaller again. The third ionization costs even more energy. So if we wanted the total enthalpy cost of 3 ionizations, we could add all these together. To get aluminum to a +3 state where it's kicked off 3 electrons. You may have to write these ionization equations, so just take note of how they're written, 1 electron at a time, and they each connect with an energy value. Here's a graphic that I pulled off the internet that kind of shows the same thing that I was drawing, but essentially each electron pulls off, the atom gets smaller. These energy values are a little bit different than the previous one just because of the source, but they're close enough to be random. All right, we're going to move on to the next page. One of the charts that you may have to read or analyze is something like this. It's going to be an atomic number versus ionization energy graph, where on the y-axis we have energy of just the first ionization. So all these elements just plucking off one electron, which I know we don't experience too much, like with aluminum. You're really only going to see it with all 3 electrons plucked off. But here, we're looking at just the first ionization. And so when we're trying to make some comparisons of, or looking at these trends and why we see an increasing value specifically on each here, we can see patterns where they're all increasing. This suggests the trend that as you're going to the right within a period, because we have period 2, period 3, period 4 shown on these graphs, as you're going to the right, in general, the ionization energy is increasing. Now we notice that there's some exceptions, which I've highlighted here or circled here. There's some few exceptions. And to really understand these discrepancies, we're going to have to look at the orbital diagrams. Now this is a method that we can expand upon when we get into electron configuration again. But just to give you the gist of it, we have the period 2 elements. The first discrepancy is between beryllium and boron, which in order, the dots represent beryllium and boron. So this is the difference between a full 2s orbital diagram, and then boron has 3 valence electrons, which we have 2s, and then there's 1 electron in the 2p block, which is going to be a 2px, 2py, and 2pz. So when you're looking at why boron has a slightly more relaxed energy requirement, boron's electron that gets ripped off is from a p orbital. There's only 1 in the p orbital. In fact, when this is removed, you still have a complete 2s orbital. And there's actually some stability in these orbitals being full. So removing this 1 electron from the px orbital in boron costs less energy than the 1 electron that's in a complete 2s orbital for beryllium. It's going to actually stress the atom out more for beryllium to lose that 1 atom or 1 electron than it would be for boron to lose that 1 electron. And that's why we see these slight discrepancies. The pattern to remember here is there is stability in half-filled orbitals or completely full energy levels. Full s orbitals or half-filled. And we're going to see another example in a second. The other example about half-filled orbitals comes from, let's go to period 2 again, this discrepancy here. It's between nitrogen and oxygen, if we're counting the atomic number correctly. Nitrogen, to focus on the p orbital, nitrogen in the p block has 3 electrons, and then oxygen, let's get that over a little bit, also has its valence electrons in the p block. Oxygen has 4 electrons in the p block, and nitrogen only has 3. So the pattern we're seeing here is it costs more energy to remove an electron from nitrogen than it does from oxygen. And this goes against the general trend where the numbers should get larger as we go to the right, where we see a discrepancy where oxygen actually gets a little bit smaller. And we can see that nitrogen starts with a half-filled p block, which is going to create extra stability. And it's going to cost more energy to remove that 1 electron from nitrogen than it is to get this electron to leave. It's going to stress out the atom more than to get that 1 from oxygen to leave. And you'd really be using orbital diagrams to describe this discrepancy. So ionization energy and electron affinity are often described as opposites of each other. If ionization energy is the energy required for an electron to leave, then electron affinity is extra energy released when an electron joins an atom. So there's a video I found that explains this reasonably well with some animations. So I linked this as well, so feel free to pop up the PowerPoint and watch this 2-minute clip. And the graphic below shows where we're focusing on ionization energy on the periodic table, where that interests us, and where we're focusing on electron affinity. Electron affinity and electronegativity are different. This one says electronegativity, but we can also use this graphic to focus on electron affinity. Okay, let's get into electron affinity a little bit. So if we were to write a chemical equation for electron affinity, it's describing when an atom, generally a neutral atom, gains an electron. Now, whereas with ionization, we split this into multiple parts, generally with electron affinity, we only look at the preferred ionization to gain a full valence electron shell. So oxygen starts with 6 valence electrons. It's going to ionize until it gains 2 electrons and get 8 total. So with electron affinity, the energy values that are provided generally just show the full gain of 2 electrons instead of breaking up into parts. Ionization energy is a little bit more common of a question to be asked about. Electron affinity is just assumed to be the opposite. Here we see a negative value for delta H because anytime a stabilization effect happens where the after state is more stable than the before state, and extra energy is generally released, which gives us a negative value. So anytime I'm talking about more stable state, generally that's associated with a release in extra energy. So that's where the negative delta H value comes from. In particular with atoms, nonmetals, they're more stable when they have that noble gas electron configuration, when they have a total of 8 valence electrons. So oxygen starts with 6 valence electrons, getting to 8 valence electrons. More stable, extra energy is released, unneeded energy. Now, something that happens with the size that we'll get into a little bit more later, but when electrons are gained, the nucleus doesn't handle the extra electrons as well. So the attractive forces between the nucleus and the electrons is spread out between more electrons. The electrons actually all start shifting away from the nucleus more and more. The atom gets larger with more electrons because that positive charge in the nucleus is spread between more electrons, and each electron feels the nucleus less, and it's able to spread out. So, size, back to size. Ionization happens, an atom loses electrons. These are going to be the metals, generally group 1, group 2, group 3. These metals will always lose their valence electrons, and as a result, the size is going to decrease. Cations are going to get smaller, anions are going to be larger than their neutral state. So, an interesting diagram that we can look at is lithium and fluorine. In their neutral state, and we're looking at the bottom diagram, in the neutral state, lithium is on the left of the periodic table, so it's a large atom, compared to fluorine, which is on the right of the periodic table, which is going to be the smallest in that period, ignoring the noble gases. When they ionize, they actually switch in roles in terms of their size. Lithium loses its outer valence electron shell and dramatically decreases in size, whereas fluorine fills up its outer shell, and as a result, in its charged state, fluoride increases in size. So you can see the difference in size when it ionizes and forms that ionic compound. The diagram on the right is a little bit clunky, but you can see the gray is the before and the red is the after size for those cations. And on the right, we've got the gray is the before, and then the blue is the after once those nonmetals gain electrons and ionize. And there's some numbers associated with the relative sizes. This last graphic is something that a tool that you can use to memorize the trends to help you refresh your memory. The big one that I try and remember is atomic radius. Now for the AP test, you're able to use some notes, so this might be something just to have readily available to you. If you remember that how the trend in size changes as you move across the periodic table, the largest atoms are on the lower left. They're going to have the smallest ionization energy value and the smallest electron affinity in the lower left. So the largest atoms are on the lower left, which corresponds to the smallest ionization energy, IE, and electron affinity, EA. And this also works for electronegativity when we get into electronegativity. Electronegativity also follows the trends. So if you remember atomic size, all the other ones have the opposite trend. Atomic radius, atomic size, again, representing the same thing. So we use this to compare atoms within the same row or the same period and justify some observations phenomenon. And these would be quick short response questions. Examples of some of the questions you may have to answer are on the classwork section right now. And I've added a feedback response so that once you type in your answer and submit it, the way the quiz works, it's not going to score you yes or no on a free response question, but I've left feedback so you can read an ideal response from me and make comparisons to how you're wording it and what you're including. During tutoring hours, which I'll open up and advertise, if you have questions about the assignments from this week, you can pop in and it's just open tutoring. We'll start doing that tomorrow. And if you're having trouble comparing your responses to my responses, pop in, or you can always send me an email as well. So I'll be lecturing on the next unit tomorrow, which will be Wednesday. My plan is to do at least 2 or 3 videos a week to help us get ready for the AP test. I'm going to finish Unit 1 tomorrow, which is mainly going to focus on electron configuration, which we saw a little bit of a preview with the orbital diagrams today, but I think the electron configuration piece is the more complicated piece, and so we'll get to that tomorrow. And then later on this week, we'll start Unit 2. Last little thing is I am going through all the progress checks on the AP Classroom through College Board, and I'm essentially closing down and reopening the progress checks. So you already submitted a lot of these from previous units earlier in the year. I am resetting those scores and opening them up again so you can go back and retest as well. So that's something you can do on the side if you're looking for some additional question types. Other than that, thanks for watching these videos, and hopefully they're helping, and feel free to email me or join these office hours I'm going to be advertising soon and get your questions answered. Hope everyone's doing okay and happy studying. See ya.
What time is the Zoom tomorrow?